So in this video we will discuss the proof of this theorem. If V and W are two vector spaces of same dimension, but the dimension should be finite. So same dimension and T is a linear map from V to W, then these following three statements are equivalent. So first statement says T is 1 to 1 if and only if T is 1 to, if and only if rank of T is equals to dimension of V. So to prove that, we need to take help from dimension theorem. So from the dimension theorem, it also called null nullity theorem. Sometimes it also called null nullity theorem, or it also called fundamental theorem of linear algebra. So according to dimension theorem, we have rank of T plus nullity of T equals to dimension of the vector space. So we know this one. Now we will use this one to prove this. Okay. Now first start from 1a. Now T is 1 to 1, the linear transformation T is 1 to 1 if and only if null of the linear transformation is the zero vector. And last video we proved this one. Okay, null of T is zero vector. Now if null of T is zero vector, then dimension, so if null of T is zero vector, then what would be nullity? Nullity of T. So what is nullity? Nullity of T is dimension of null of T. Okay. So if you take dimension of this one, so it would be nullity of T. And how about the dimension of zero vector? Dimension of zero vector is 0. So it is 0. That means we take dimension on both sides. The dimension of nullity is dimension of null space is nullity of T, we can write, and dimension of zero vector is 0. Okay. Now if nullity of T is 0, then if nullity of T is 0, then rank of T equals to dimension of V. Okay, we can write here if and only if. So if nullity of T is 0, then rank of T equals to dimension of V. And this one is C. So we proved C. Okay. So we start from A and we proved C. And rank of T, we know rank of T is dimension of range of T. Okay. So this one is dimension of range of T equals to dimension of V, because we know rank of T equals to dimension, by the definition of rank of T, dimension of range of T. Okay, rank of T equals to this one. Now if dimension of range of T equals to dimension of V, then this implies range of T equals to V. Range of T equals to V. Now why? Because range of T is subset of or subspace of V. If dimension of two vector space are equal, that doesn't mean they are equal. Okay, dimension of range of T and dimension of V are equal, Now we write range of T equals to V. Why? Because range of T subspace of V. If one is subspace of another one, if one is subspace of another one or subset of another one and their dimension are same, then you can write they are equal. But in general, dimension are same doesn't mean they are equal. It like one condition should be one should be subset of another one. Okay. So range of T equals to V, and if range of T equals to V, that means T is 1 2. Okay. So it means T is 1 2. So it proves B. So we start with A, that means T is 1 to 1, and by the definition of 1 to 1 linear map, if T is 1 to 1, then null of T is 0 vector. We take dimension on both sides. The nullity of T is 0 because dimension of 0 vector is 0. And if nullity of T is 0, then from this one, from dimension theorem, we got rank of T equals to dimension of V. So it proves part C. Now rank of T is dimension of range of T. So this one. And since range of T is subspace of B, subspace of the vector space B, and since the dimension are same, so one should be same as another one. Okay. And if range of T equals to V, it means that the linear map is 1 2. So again, this theorem is true only for finite dimension. For infinite dimension, this is not true. So thanks for watching.